Okay, so we are almost at the end of this chapter of introduction. Let's look a little bit more at plants and how they affected the Earth's environment. This schematic here shows that you have phytoplankton in the ocean, which are autotrophs, so they photosynthesize, so they remove CO2 from the atmosphere, which is abundantly available as dissolved CO2 in the ocean. It's not a trace gas in the ocean, unlike the atmosphere. And whatever photosynthesized material, carbohydrate that is produced, a lot of it is of course consumed by zooplankton, and there is a food chain that is supported by primary production or photosynthesis of phytoplankton. Any molecule of carbohydrate that escapes consumption and goes to the bottom releases O2 in oxygen into the atmosphere, and the carbohydrates that fall to the bottom of the ocean go through various processes and can form oil, natural gas, and so on. And on land as well, you have photosynthesis by plants, which remove CO2 from the atmosphere, and whatever falls on the ground and gets buried or sequestered can end up becoming over time coal seams and so on. So historically speaking, there are large reservoirs of oil and gas and coal formed over millions of years, what we call geologic time scales by various processes. And the interesting tidbit there is that the termites evolved around 120 million years ago, and they started to consume some of the carbohydrates that is buried in soil. So they started to convert it into methane. So fossil fuel formation in some sense has been reduced by termite evolution over the last 120 million years. But the fossil fuels that we are burning are formed over a very long time. So we keep talking about the past, when life evolved, how continents got formed and moved around, how plants have evolved, how our atmosphere has changed, and so on. How do we know this? The briefest introduction we'll have here is that this is done via what is called radiometric age dating. So there are certain elements that can spontaneously change or decay, which means they go from one element to another spontaneously. They are called radioactive, and they have a so-called half-life, which means if you start with 100 atom of an element that's radioactive, the time it takes for it to reduce to 50 atoms is called its half-life. It keeps decaying, but it is this half-life that can be used to estimate the time period that has passed for any particular process or material we are looking at, any chemical evidence that we are diagnosing. So using these kind of radiometric age dating, we can estimate that Earth is about 4.6 billion years old. We say about because the data still keeps coming in. You look for the oldest rocks, we try to date them, and so on. So the concept is simple. So you start with uranium-235 atoms, which are a million in number, let's say. 235 is the atomic number, and it decays spontaneously into lead-2007. So you need to figure out the half-life of uranium-235 to go into lead-2007. So you look at a million uranium-235 atoms, which has 0 lead-2007 atoms, and in a 500,000 years, so going from, in about 0.7 billion years, going from 4.2 billion years ago to 3.5 billion years ago, uranium-235 has gone from 1 million atoms to 500,000 atoms. So this is one half-life, and in two half-lives it has gone from 500,000 to 50,000, and lead has gone from 500,000 to 750,000. So you can see that it occurs from 3.5 billion to 2.8 billion. So you can go forward and see 3 half-lives, 4 half-lives, and so on. How do we know this? Basically, you need to find reservoirs which are unperturbed. So there is no source of uranium, there is no sink other than radioactive decay to lead, and that allows you to estimate the original amount that would have been there and what you ended up with after so many half-lives. So today we have had 6 half-lives of uranium-235, and it has gone from 1 million atoms at the beginning at 4.2 billion years ago to 15,625 atoms now at present. Okay, so this is how you do it. There are lots of details, there are lots of issues, lots of uncertainties, accuracies, and so on, but nonetheless, this is a very reliable, very calibratable, accurate, precise method which actually can tell you a lot about the past history. So based on these kind of techniques, the geologists have created eons, eras, and periods, and so on. So briefly speaking, you have the Precambrian, which occurs before about 540 million years ago. After that, you have Phanerozoic, which consists of several eras. Why is it called Precambrian? Because this happens before the Cambrian, which started around 540 million years ago. Phanerozoic means visible life. So the Precambrian is divided into Hadean, which is a Greek word for hell, where the primordial soup stage of the Earth existed, meteorites were crashing into Earth, there was volcanic activity and so on, and there was no life as far as we know right now. And Archean comes from the word arches, which means the beginning, which is the earliest evidence of life we have, about 3.8 million years ago. So you have early Archean, middle Archean, and late Archean, and you have Proterozoic, which is early life, where we have clear evidence of life forms early on, about 2.5 billion years ago. So you have early Proterozoic, middle Proterozoic, and late Proterozoic. Phanerozoic is visible life, where you have visible evidences, fossils and other things that can be used to look at life. So Cambrian is where there was a huge explosion happened, so starting here on the expanded section of this part. Precambrian Proterozoic ended around 540 million years ago. Before that, you have some evidence of life in Ediacaran. There are many details. These used to be more radially symmetric, so things like jellyfish, which have up and down, but they don't have a right and left, to bilateral symmetry like insects, and we have a left and a right, for example. There are genetic details on how that happened, etc. But Cambrian corresponds to an explosion of a large number of species. By estimates, 25 million new species evolved around that time. So we consider all the period before that as Precambrian, and the period since then as Paleozoic, Mesozoic, and Cenozoic, or largely the eon Phanerozoic. So you can see that the odd mesh-like creatures in the Ediacaran, that's a place in Australia, first organisms with shells appear. There are details about why shells appear: to avoid predation, being eaten, because some other species would have evolved ways to bite or dissolve shells, and so on and so forth. Then various species, fish, insects, amphibians. Then we have the age of the dinosaurs during the Triassic, Jurassic, and Cretaceous. There have been several mass extinctions along the way. We know we have had 5 mass extinctions along the way. End of the dinosaurs, basically, by the meteorite crash during the Cretaceous extinction, led to domination of the mammals. And on this time scale, Holocene is just a tiny, tiny, tiny fraction where humans evolved. But now we are the dominant species. We are consuming energy at a tremendous rate compared to all species in the history of Earth, right? So the philosophical questions arising out of that would be, are we supposed to have evolved to consume energy to join the race of dissipating energy in the universe, or are we just out of control? Are we going to destroy ourselves? Are we going to destroy our home planet, and so on and so forth? But those are not within the scope of this course, so I will stop with this. This essentially ends the chapter. I will show one animation, and then we will conclude this